Welcome back, everyone, to a brand new explainer. We're doing something a little different today. Welcome to our Summer of Battery Chemistry and Corrosion. I know, it sounds intense, right? But honestly, it is. We're about to look at this totally invisible, thermodynamic battle that's happening all around us, literally right this very second. It's a massive showdown between the creation of power and the absolute relentless destruction of materials.
Let me just ask you a quick question to get things started. What connects a dying phone battery, right when you need it most, to a massive, rusting shipwreck sitting at the bottom of the ocean? It seems like a huge stretch, right? But here's the wild part. These two completely different scenarios are actually just two sides of the exact same electrochemical coin. It's all about how electrons move, and today we're going to master exactly how that works. Okay, let's dive into this. We need to establish the heroes of our first act, the battery. Think of a battery as basically a packaged, carefully controlled chemical reaction. The basic anatomy consists of three main components. First up, we've got the anode. This holds active materials that spontaneously undergo what's called oxidation, which just means it releases electrons. Then we have the cathode, and that undergoes reduction, meaning it readily accepts those electrons. And sitting right between them is the electrolyte. That's a chemical medium that facilitates the migration of ions. So this whole setup is where spontaneous redox reactions occur, physically pushing electrons through a wire to power your life. Now, obviously, not all batteries are created equal, right? We generally split them into two functional categories. Over on the left, we've got primary batteries. Think of your standard alkaline AA batteries, like the ones in your TV remote or a wall clock. They're single-use, non-rechargeable, and perfect for low-drain devices. The chemical reaction only goes one way here. Once those active materials get consumed, the cell is entirely dead and it just goes in the bin. But on the right, we have secondary batteries. These are the big rechargeable powerhouses used in multi-cycle, high-drain applications. By applying an external electrical current in the reverse direction, we literally force those inactive materials to convert right back into active ones. We're manipulating chemistry here to store and release energy over and over again. And when it comes to those secondary rechargeable batteries, there are two absolute heavyweights that make our modern, super fast-paced, portable life possible. I'm talking about the massive batteries powering our cars and the tiny ones keeping our cell phones alive all day long. Let's look at how these titans actually work on the inside.
So this brilliantly illustrates the architecture of the classic lead-acid cell. The battery that sparks your car engine to life every single morning. Inside, you've got these alternating plates. The anode is made of grids of spongy lead, and the cathode is packed with lead dioxide. These really heavy alternating grids are suspended in an electrolyte bath of about 20% sulfuric acid. When you turn your ignition key, the battery discharges, creating lead sulfate and releasing a massive instant surge of electrons to start the motor. But then, as you drive, your car's alternator pumps electricity right back in. It acts as an electrolytic cell, reversing that chemical reaction so it's ready for your next trip.
Now, let's shrink things way down to the smartphone sitting right there in your pocket. That device relies on a lithium-ion cell. Interestingly enough, it doesn't actually contain metallic lithium at all. Instead, it relies entirely on the movement of lithium ions. Notice how the positive electrode is made from layers of lithium cobalt oxide, and the negative electrode is made of layers of highly porous graphite carbon. They sit in a polymer gel electrolyte completely separated by a perforated plastic sheet. So, when you're scrolling through social media and draining that battery, lithium ions are flowing from the negative to the positive electrode. Then, when you plug it into the wall at night, the electrons and ions are pushed right back. It's this incredibly rapid, continuous, microscopic shuttle of ions keeping you connected. So, the crucial point here is, all of this amazing, world-changing battery technology relies on highly refined, highly reactive metals to hold and move that charge. But nature doesn't really like that. As our source material brilliantly and pretty bluntly states, corrosion is an oxidation process, and it is the reverse of metal extraction. Think about it. We spend massive amounts of energy to extract pure metals from stable ores in the earth. Those isolated pure metals are essentially in a highly excited state, and thermodynamically, they just want to go back to sleep. They desperately want to return to their natural, stable, combined state. Which brings us to Act 2 of our summer explainer, the silent destroyer. Because while batteries harness oxidation inside a closed, controlled system, corrosion is that exact same electrochemical decay happening out in the wild, completely uncontrolled. Let's look at exactly how this microscopic sabotage actually happens. During the dry oxidation of a metal, the metal atoms at the surface lose electrons. They oxidize, becoming positively charged metal ions. At the exact same time,
Oxygen from the air swoops in and takes those newly freed electrons, becoming negative oxygen ions. And because of that charge difference, these ions diffuse towards each other. Right where the metal ions and the oxygen ions finally meet, boom, they form a metal oxide. That is the destructive scale, the rust, the tarnish, that literally eats away the pure metal surface from the outside in. It's basically nature actively taking its energy back.
And the casualties of this invisible war are massive. We're talking about the literal wastage of metal as it dissolves back into chemical compounds. But it's not just about losing material, right? It's about losing the functionality that makes metals so useful to us in the first place. Corroded metals lose their vital electrical conductivity, their malleability, their ductility, and their structural strength. This drastically reduces the lifespan of our buildings, our bridges, and our vehicles. Ultimately, it leads to the unpredictable and often catastrophic failure of really expensive machinery. It's a massive physical and economic drain on our global infrastructure every single year.
But hey, don't worry. Human ingenuity doesn't just sit by and let rust win. This brings us to the counterattack. Engineers have developed some seriously brilliant ways to fight back against this thermodynamic decay, essentially using the environment's own electrochemical rules against itself. Since corrosion always happens at the anode part of a metal, the part where electrons are lost, what if we could force our important structures to act purely as the cathode? You know, the part that receives electrons and stays perfectly safe? Well, this genius strategy is called cathodic protection.
Here's exactly how we pull this off, using a method called sacrificial anode protection. Step 1. We take the valuable base metal structure we actually want to protect. Let's say it's an underground steel pipe, and we physically connect it by an insulated wire to a much more chemically active metal. Step 2. Because the attached metal is more active, it forces our really valuable pipe to behave entirely like a cathode. It just sits there and receives electrons instead of losing them. And step 3, the active metal becomes the anode. It literally sacrifices itself, corroding away into absolutely nothing, just so the main structure remains completely untouched. We're basically redirecting the destructive flow of electrons to a decoy.
Now, what's really interesting about this is how this incredible engineering looks in the real world, on a massive scale. Take an ocean-going ship's hull. The hull is made of steel, and it's constantly submerged in harsh, salty seawater that is practically begging to corrode it. But look at those blocks attached to the side. Those are blocks of magnesium, a highly active metal. The magnesium acts as our sacrificial anode. It gladly gives up its electrons and slowly dissolves into the ocean, providing a constant flow of protective electrons to the steel hull. So, as long as those magnesium blocks are there taking the hit, the steel hull simply cannot rust. It is such an elegant, highly effective chemical shield.
It's truly incredible engineering, but looking at the big picture leads us to a fascinating final thought to wrap up this explainer. Are we ever truly defeating corrosion? Or are we merely pausing the inevitable return of these metals back to the Earth? Whether we're harnessing chemical oxidation to power our cell phones and cars, or sacrificing blocks of magnesium to protect our global shipping fleets, we're really just temporarily borrowing energy from nature. These invisible chemical wars are happening all around you, every single second. So next time you charge your phone or see a rusty nail, I hope you remember the incredible thermodynamic battle going on right beneath the surface. Thanks so much for joining me for this deep dive, and as always, keep questioning the world around you.